Welcome to Lyons Township High School, AP Physics 1. Got an example today. This will be a moderately long one, so hang in there, guys. But this is a good one. There's a lot of review in this one, and we're going to discuss several topics involving work and energy. So, specifically, here's what we got. We got your backpack. Okay, I drew it as a box, but it's your backpack. You push it up against a spring, and you compress the spring some distance x. You then let the spring go, and the spring is going to shove your backpack. Your backpack's going to now have a flying start. Your backpack's going to skid along level ground to point C, and then it's going to encounter an incline and go up the incline, and eventually at point D it'll stop. Okay? I've labeled some stuff on here. That's X, that's how far the spring was compressed. D is from the end of the uncompressed spring to the bottom of the incline, and then D sub S is the stopping distance up the incline. Some stats. The spring constant for the spring is 10 kilonewtons per meter. You compress to 20 centimeters. This distance here, D, is 4 meters. The backpack mass is 10 kilograms. Coefficient of sliding friction is 0.25. And the angle of the incline will make it a nice ubiquitous 30 degrees. Some things we're going to figure out. How fast is your backpack going at the moment it's released from the spring after it's gone that 20 centimeters, okay? How fast is the backpack going when it gets to the incline, the bottom of the incline? And how far up the incline does the backpack go before it comes to rest? So what I would suggest you do, one more thing. We're going to talk about, while finding those numbers, we're going to talk about the following things. During what parts of the process, A to B, B to C, C to D, is energy conserved? The second question we're going to answer is same question, but we're going to change it to mechanical energy. During what parts of the process is mechanical energy conserved? And finally, we're going to discuss the energy transformations, okay? So you might want to spend a moment, make sure you have all that copied down, and then we'll get going. All right, so hopefully you got all that copied down. We'll start with doing the numbers, okay? So we are going to figure out, using energy, we're going to figure out the velocity of the backpack at point B, the moment it's released from the spring. So we're going to use conservation of energy. And we're going to go from A to B. Okay, so when we do conservation of energy, we say kinetic energy at A plus potential energy at A plus any work done by non-conservative forces equals the kinetic energy at B plus the potential energy at B. Okay. Now, I always start by, knocking stuff off. So, for instance, at point A, the box ain't moving, or the backpack's not moving, so there's no kinetic energy at A. There is potential energy, though. And there's two kinds that we deal with. There's gravitational and elastic, aka springs. And we got spring in this case, so we're going to have a term there. There is work done by a non-conservative force. So what forces act on the backpack as it slides from A to B? Well, you got the spring pushing on it. That's what we call a conservative force. That's going to be in the potential energy term, so we don't put that in for work non-conservative. We got the normal force acting, and the normal force is a non-conservative force. The ground is pushing up on the box, but is the ground doing any work on the box? Is a normal force doing any work on the box? Well, the box is moving right, the normal force points up. Since the normal force is perpendicular to the backpack, the normal force doesn't do any work on the backpack. You have gravity, which is a conservative force, so we don't put that in a non-conservative work term, but even if you did, it wouldn't act in this case because gravity is also acting perpendicular to the motion of the backpack. And then you've got friction. Friction is acting parallel to the backpack's direction of motion, and it is doing work on the backpack, so that's going to be our non-conservative work term. When the backpack gets to point B, it does have kinetic energy because it's moving and we're trying to find its velocity there. There is no potential energy, though. The spring is now uncompressed and there's no changes in height in this problem, okay? So there's a term here, there's a term here, there's a term there. This is 0 at point B, okay? Potential energy for a spring, what's the equation? Well, it's 1/2 kx squared. And I'll put x sub a, okay? Work non-conservative. Well, first of all, is that work going to be plus or minus? Well, friction is acting in the opposite direction of the motion, so it's going to be minus. In other words, friction is going to suck energy out of our system. And we'll talk about what happens to that energy in a minute. So it's the work done by the force of friction. At point B, the box has kinetic energy. The equation for that is 1/2 m, and I'll put velocity at B squared, okay? Now, the work done by friction, okay? So I'll write that out a little bit. The work done by friction is the force of friction times x, force times distance, okay? The force of friction is mu sub k times Fn. And then we have to have our x, okay? Now, in this part of the problem, what's Fn? Well, hopefully you recognize that there's no vertical forces acting on the backpack except for weight and normal force. And since the backpack, now there's a lot of ifs here, but because the backpack is not accelerating up or down, and because there's no other vertical forces besides weight and normal force, the normal force will equal the weight of the backpack. So, and again, that's only true because all those ifs are satisfied. Okay, so Fn, this equals mg. So the size of the work done by the force of friction is mu sub k times mg times x. So we put all that in for this right here. And we still have the negative sign out front because that work is going to be negative. That's going to suck energy away from our box. So if we put all that down here, we get 1/2 kx at a squared minus mu sub k mgx equals 1/2 mv at b squared. And looking at all that, the good news is we have all those numbers. Also make a note, there's nothing here that we can really cancel. Like for instance, there's an m here and an m here, but there's no m there, so we can't cancel m. You have to have it in all the terms. There's nothing in all three terms. So I'm going to plug numbers in, and what I want you guys to do is we're going to get a number for this, a number for this, and an expression for that. And I want to talk about these numbers. All right, so this number here, 1/2 k. Well, I said it's 10 kilonewtons per meter. A kilo is 1,000. So this is 10,000 newtons per meter times 0.2 squared minus mu, which was given as 0.25. The mass of your backpack is 10, g is 9.8, and x is given as 20 centimeters, which is 0.2. We also did that here. That's 20 centimeters, or 0.2 meters, equals 1/2 the mass of the backpack's 10, v sub b squared. Okay, so thankfully our numbers are actually pretty easy here. 0.04, half of that's 0.02. 0.02 times 10 grand is 200. If you multiply all that out, you get 4.9, and you can satisfy yourself that way. This is the kinetic energy at B. So here's what I want to do. I want to write kinetic energy at B. So if I subtract those, I get 195.1 equals the kinetic energy at B. I want to make some notes here. Was energy conserved going from A to B? Well, you're darn right it was, because we got an equal sign here. Okay, in other words, is this all equal to that? Well, by definition it is. So energy is conserved. Now the other question is mechanical energy conserved in this problem? And remember, mechanical energy, I'll write that off to the side here, mechanical energy is the sum of your kinetic plus your potential energies. Well, before I started, I had potential energy, and that number is 200. This system started off with 200 joules of energy. After it's moved from A to B, well, now it's only got 195.1 joules of mechanical energy. So we lost some mechanical energy, okay? We lost 4.9 joules of mechanical energy. what happened to that 4.9 joules? That is the work done by friction, and that is turned into thermal energy or heat. So of our 200 joules, we lost 4.9 due to thermal energy or heat. The rest, 195.1, that is kinetic energy in the box. So energy is conserved, but mechanical energy is not. Okay, so that's our velocity. Oh, we got to find our velocity at point B. That's easy enough. So again, this is equal to that. So I'll write that down. 195.1 equals 1/2 times 10 times v sub b squared. You might want to try that in your calculator, but the velocity at B, when I plug those numbers into my calculator, I got 6.25. 6.25 meters per second. So your backpack is moving, that's about 14 miles an hour or so down the hallway, let's say. There you go. All right, so that's at point B. Now, the next question, numerically we asked, is what's the velocity of the backpack at point C right before it hits the incline, okay? You have a couple options here. If you're using energy, and when we ever reuse this equation, by the way, and I'll even write it up here as reference. So we've got kinetic energy at some start point plus potential energy at some start point plus some work, non-conservative, equals some kinetic energy at some final point plus some potential energy at some final point. You got to pick the 2 points you're going to study. What's the starting point? What's the final point? Work non-conservative is simply what happens in between your starting point and your final point. So in this part of the problem, we can either go from A to C or from B to C, and either one will give you the right answer, and either one's fine. I am going to choose to go from A to C because I already got a whole bunch of information about A, and I don't even have to there's some stuff I don't have to calculate, okay? So I'm going to go from A to C, and I'll even mark that down. Okay, so if we go from, if we go from A to C, all right, so well, we're going to write conservation of energy down. Kinetic energy at A plus potential energy at A plus any work, non-conservative, equals the kinetic energy at C plus the potential energy at C. Well, the left side of our equation will be very similar to the last problem. There's no kinetic energy at A. It wasn't, the backpack wasn't moving yet. This is spring potential energy, okay? This is the work done by friction, but it's not that 4.9 value. Okay, last time we got negative 4.9 joules here. Well, now it's going to be much bigger because the box is sliding much further, okay? At point C, the box is moving because we're asking for the velocity there, or we hope it's moving there. There's no potential energy at point C. The box is, or the backpack, I keep saying box, the backpack hasn't gained or lost any height. The spring is uncompressed now, so this term is 0. So this looks very much like the last part of the problem. U sub A is 1/2 k xa squared, which we already know the value of that's 200. We already got that value, okay? Okay, first of all, it's minus because it's the work done by friction. We already talked about that in the last step. It's the force of friction, which is mu sub k times mg, that's like before. But what do we put in for the distance here? Okay, is it x, like we did last time? Okay, well, not quite. If the box is going from A to C, we need this whole distance, which is x plus d. So I'll write that in here. This is x plus d, okay? At point C, we have kinetic energy. I'm just going to call that K sub C for now. We'll get a number for that, and then we'll find velocity in a moment. All right, so I already know this is 200, so I'm just going to put that in here. Minus mu sub K, which is 0.25, m is 10, g is 9.8, x is 0.2 meters, so 0.2, and then d is 4. So that's 4.2 total meters, and that equals K sub C. All right, so you end up with 200 minus, when I plug all these into my calculator, I got 102.9 equals K sub C. So the kinetic energy at point C is 97.1 joules. Now, check this out. We started with 200 joules of total energy in our system, and we're down to 97.1. What happened to the rest? Well, we have lost now 102.9 joules of energy due to friction. Over half of our energy is now gone. It's turned into thermal energy. So again, mechanical energy is conserved because if this side of the equation equals that side of the equation, energy is conserved, okay? We lose mechanical energy though. The total potential and kinetic energy before was 200. The total potential and kinetic energy after is only 97. We've lost over half of our mechanical energy. So again, it's a little confusing. Energy always conserved. Mechanical energy not always conserved, okay? Now for velocity at point C, that's easy enough. Velocity equals the square root of 2 times the kinetic energy at point C over m, which is root. And again, if you solve kinetic energy is 1/2 mv squared. If you get v by itself, you get that expression. You take 2, the kinetic energy is 97.1 over m, which is 10. And when I plug all those numbers into my calculator, I got 4.41 meters per second. So the backpack has slowed down quite a bit since leaving the spring. Okay. Now, finally, I asked you about how high up the ramp does the box go, okay? To get from, so now we're going to go from, you can go from A to D, you can go from B to D, or now we can go from C to D. I'm going to go from A to D. I'm going to choose that because I've already got a whole bunch of information about A, okay? So, I'll make some room up here. All right, are you ready? All right, so we're going to go from A to D now, the whole entire motion of the backpack, okay? So, and we're going to use conservation of energy. So kinetic energy at point A plus potential energy at point A plus any work done by non-conservative forces equals the kinetic energy at D plus the potential energy at D. Let's go ahead and knock out our zeros. At point A, the backpack wasn't moving yet. That was when it was pressed up against a spring, so that's 0. The spring is loaded, so there is potential energy. There is work done by friction. At point D, we're saying how high does the crate or does the backpack go before it stops? So at the moment it stops, that kinetic energy is going to be 0. At point D, will there be potential energy? Well, the box has now gained height. So there will be potential. Specifically, there'll be gravitational potential energy, okay? So I'm going to write a line, one more line down here. We're going to say U elastic at point A plus any work done by non-conservative forces is going to equal U gravitational at point D, okay? Now, this number I know. It's 1/2 kx squared, which is 200. I already got that number. This gets a little tricky, okay? This is going to be 2 terms, okay? There's the work done by friction going from here to here, which you already know. We got that in the last step. It was 102.9 joules, so that's minus 102.9. But then we also got friction is going to do negative work from here to here, okay? That's going to be a different number, and you got to do a little bit of work, no pun intended. But you got to do a little bit of work there too, because now friction, the force of friction is going to change because now we're on an incline, okay? So here's what we're going to do. Here, this is 1/2 kx squared, x sub a squared, okay, minus the work done by the force of friction from A to C, which I already know, it's 102.9. Minus the work done by the force of friction from C to D. That number I don't know, okay? That's going to equal gravitational potential energy, and this is an equal sign here, and that is equal to mgh at point D, okay? All right, so a couple numbers I know. I know this is 200. I know this is 102.9. I already got those numbers in the last step, okay? This is going to get a little tricky. This is minus the force of friction times d stop. Okay, force times distance. And that's going to equal mgh. All right, I'm trying to find d. this is d sub s. What's h? Okay. Well, if I have d sub s, h is the hypotenuse times, that's the opposite leg, so sine of that angle. So h is going to be d sub s sine of the angle. So h turns into d sub s sine of the angle. So I'm going to have my unknown in two spots, okay? But the rest of the numbers I'm going to know, all right? Force of friction. Let's draw an FBD of the backpack as it's sliding up the hill here, okay? And I'm going to draw it in component form right off the get-go. So while the box is sliding up the hill, you're going to have the normal force acting on it. Now, in this case, will the normal force equal mg? Will the normal force equal the weight? Well, hopefully you know it doesn't, okay? You're going to have the weight of the box, which points down. We're going to split that into components. We have mg cosine theta and mg sine of theta. And we also have friction acting on the box. And the box is sliding up. Friction acts opposite that relative motion, so the force of friction acts downward. So hopefully you'll recognize that this force is going to equal mg cosine theta because the backpack is not accelerating this way, nor is it accelerating that way. So these two forces have to be equal. These two forces do work. Now, you don't put this in the non-conservative term because that's a conservative force. That is going to become your mgh. So you don't worry about that. Friction is a non-conservative force, so friction is going to do work. I'll calculate that force really quick. Force of friction equals mu sub k times Fn, which is mu sub k times Fn equals mg cosine of the angle. So we will put that right here, okay? So here we go. We got 200 minus 102.9 minus force of friction, which is mu sub k times mg cosine theta times d sub s equals mg. I'll reverse this. I'll put the sine of theta first, and then d sub s after. I just flip those two over. Now, having said all that, can you cancel the mg's out here and here? No, because there's no mg here and here, okay? So you can't just go canceling stuff unless it's in all the terms, and we don't have anything in all the terms. So, but we have numbers for everything in this problem except for ds. So, this is 200 minus 102.9 minus 0.25 times m, which is 10, times g, which is 9.8, cosine of 30 degrees. All that, this is 0.25, times ds equals m, which is 10, times g, which is 9.8, sine of 30, okay, times d sub s. All right. Then we have 200 minus 102.9 minus, if you plug all these numbers in the calculator, I get 21.2. You might want to check that. So that's 21.2 ds equals, and then this term is 49 ds, I believe, yes. 49 ds. All right, so now we're just doing algebra. This is 97.1 equals, if I move this over to here, you get 60, 70, you get, or 70.2 d sub s, okay? And if you divide both sides by 70.2, you get d sub s equals, I get 1.38 meters, okay? So that's how far up the box slid up the ramp before it stops. A little over a meter. Okay, so not all that far. That's about 4.5 feet. Okay, so now real quick, if you take that number and plug it back into here, okay, what's this whole term equal? Well, it turns out it equals 29.3. So this is 29.3. And if you take that ds and plug it into here and get a number there, so you take 49 times 1.38, you get 67 69.8. Okay. There's a reason why you might want to write those numbers down or think about them really quick. So we got 4 numbers up here. What do they represent? 200. That's the starting potential energy of the spring. That's the total energy in your system at the beginning. 102.9. That's negative. That's the work done by friction as this thing moves from A to C. So friction sucks out 102.9 joules of our 200 by the time we get to there. What's this negative 29.3? Well, that's the work done by friction when the box goes from here to here. So the friction takes out another 29.3 joules of energy. What's the 67.8? That's how much energy is left. Mechanical energy is left. That's the gravitational potential energy of the box at the time it stops. So it started with 200 joules of mechanical energy. It only ends up with 67.8 joules of mechanical energy. So energy was conserved, okay, but mechanical energy definitely was not, okay? So it does help to look very carefully at all the numbers and think about what each number means in the problem. So that was a long problem, but that's a great review problem. I hope that was helpful, and thank you very much.